Today, I want to talk about languages, specifically compiled versus interpreted languages. Uh, you see, the goal of writing code is eventually to end up with machine code that is directly executable by the CPU to which this program was executed or compiled against. So if all of us knew how to, if all of us knew how to program in machine code directly, none of the languages, and there was no barriers at all, none of the languages were existed. Languages existed mostly for ease of use and, to remove the barrier of entry, because writing machine level code is so complex. Plus, there are a lot of CPUs, different machine code, different native level instruction per CPU. So languages are useful, needed. But if this didn't exist, we wouldn't need languages. So the goal of all the languages that we build and write code against is to get that machine code which executes the instructions, the code that we authored. So that's the goal. And for the longest time, we only had one way of doing that. And I'm going to skip, perhaps it's an honorable mention to mention assembly, which is the closest, almost one-to-one universal language that works on any CPU. So you learn assembly, and if I give you an instruction, that instruction will work on all other CPUs if you compile it to the machine language. So that's the closest level, but it's very hard to get right? Because you need to do so many work to do so simple things. But then a high-level language were invented to simplify this even further, right? To allow us to do complex things that are not really easily doable. And that's C. Right? Of course, I'm not going to go through history because I'm not really interested in the history first place, and I don't really know it. Right? But C is one of the first languages that are compiled. So you learn C, and you learn how to write in C, and eventually you write certain code. I want to add 2 numbers. You define these concepts of variables and data types and whatnot, and the language tells you how to allocate memory, deal with arithmetic operations, and tells you like, hey, this plus sign, this actually, it doesn't exist, right? It's just a symbol that the language created, and that gets, when you compile it, gets translated to a specific machine code that means addition, right? So that's what this is all about. So compiling a language will generate a machine code binary that executes natively, directly on that CPU. Very powerful. It's as fast as it gets. But as I always say in this channel, there is the cost of abstractions. Because the language is an abstraction, you simplified something, but at a cost. And that cost is you're hiding things. So back to when I started this video, and I said, if we really knew how to write machine code, there wouldn't be any, problems with performance, or this language is better than this. Why? Because, well, we're gonna write the minimum number of instructions to do X. That's it, right? But languages add complexity, they hide things. And some languages, of course, when you compile something to that machine code, it generates, it tries to do what what you give it, the instructions you give it. But that tend to be complex because it's a high-level language. You're almost talking human, right? And then you're trying to convert it into machine code, which is a very simple set of instructions, whether you're coding against REST, reduced instruction set, or CISC, which is the complex instruction set. But regardless, you're doing that. So now, any language you use is going to introduce that overhead. And languages and compilers, bread and butter is to compile the best optimized code. And it solves like silly mistakes that we make in the program, like defining a variable that we never use, or doing a function that we never call, or returning early, and the rest of the code that is below the return is actually never executed. So we're never actually generating. We don't need to generate that code to begin with because it's never going to be executed, and so on. We'll try to do all these optimization. Inlining is another example, right? Like when you call a function, the concept of function doesn't really exist per se, right? A function is just literally a bunch of code that lives in the text area in your process. And when you say call this function, the program counter literally jumps to that location, right? It's set to that address in memory where your function starts. That's all what it is, So calling a lot of function is another abstraction which makes you jump between all these memory addresses, like, oh, I'm calling this function which calls another function, and you're finding yourself reading from different sets of memory addresses in the process code or text area, which causes a lot of memory accesses which are slow when it comes to the CPU. And that's why I see some CPUs compile it with concept of inlining. I said, all right, you call this function a lot in a loop and you're gonna be jumping over and on, so I'm gonna literally copy the code when I compile it inside that call, and instead of actually jumping to the location, I'll duplicate the call on compilation. So this is what the compiler does, which is amazing, right? So we have these compile languages, and we've been using them, and there are like many other compile languages. And C was one of the languages that you have to do your own memory allocation and deal with. If you declare something, you have to clean it up. And in the beginning, that kind of makes sense. So, all right, this is things that you have to do. It's just right. You declare the variable or an object, you have to remove it from memory. So part of this, let's say, concreteness of the memory and the CPU is being exposed to the user, this memory allocation, which can lead to problems, right? Problems in memory management, because now you're putting the onus on the user, or the developer in this case, to clean up after itself, to correctly, remove memory, to deal with all this, which is difficult. Then were born languages. That's why languages were born that manage memory for you. So, all right, let's build another set of compile languages that manage memory for us. Like it's called the garbage collection based languages, Java and Go and whatnot.
He's like, okay, scared. Yeah,
so you see the pattern, right? We're trying to simplify things as much as possible. But then the problem comes with compile languages is if I compile something, that program only works for the CPU that I compiled it with. It will never work on another CPU. Also, if I compile for Intel, it will not work on ARM. And if I compile in this It will not work on Mac M1 and so on, or Windows EXE. It won't work on Linux. You get the point, right? So then another set of languages were born, which are called the interpreted languages. Mainly Python and JavaScript come to mind here. And the beauty of these languages are they are CPU, agnostic. They're not really compiled. So what you do instead, and you can argue that Java is actually one of these languages as well. It's not really well, it is in a sense because it uses Java JVM, right? But JavaScript and Python work on any. If you write a Python script, you don't compile it, right? As long as the Python library, what's called the runtime exists, it runs. JavaScript code, if you have a node runtime or bun or deno, it just runs, right? You still need this extra thing that's called the runtime. If you have Java, then you need this Java runtime. So, but it's slightly more, portable, if you will. But the hit with interpreted languages, because they are not compiled, there is this intermediate step, right? So there is this runtime that exists that knows how to understand the code you wrote, which is the Python code. So if I say A plus B in Python and I run this program, it is not directly translated to a machine code, A plus B, directly. No, the Python runtime or the JavaScript runtime, this think of it like an interpreted language. Any interpreted language works the same way. It looks at your code and it's not really looking at it as a string. It is another level called the byte code, where it looks like, all right, you have this plus sign. This plus sign is actually this code over there. Right? So there is this, and then the code, the machine code gets executed. See, there is like an extra step to this interpretation step, where I see this plus sign, this means this. I see this declaration, this means this. So there is like F and then F. Think of it like this. So there is the interpretation step, and then the extra step is the actual execution. That's why people say interpreted languages are slow. And that's the reason, because you're not really executing directly. You're doing a step to interpret in order to execute. Versus if it's a machine code, no, it's ready. The machine code, the compiled executable, is ready to be executed. It's literally loaded in memory as machine code, as CPU instruction. So all we have to do is just literally pull that thing into the IR, which is the instruction register in the CPU, and then boom, the CPU executes it. Of course, that's why programs have to be compiled to the CPU that you're compiling against, because you're directly compiling against that. And that's why it has to work like that. Okay? Versus interpreted languages, where there's this extra step that you need to essentially translate this string or this language that you have into whatever the Python runtime or the JavaScript V8 runtime knows what it is, and then execute it. Does that make sense? Now the final thing, because I end the video, is what is called the just-in-time compilation. Yeah? So we talked about ahead in time of compilation, which is like, hey, let's compile, get something. Then we talk about just-in-time compilation. So JavaScript and Python, I don't know if Python supports that. I don't think it does. But even Java does the concept of, because interpretation is slow, it analyzes, all right, the V8 will look at this, this piece of code is executed a lot. So I'm going to literally take that and do a just-in-time compilation into whatever the current CPU instruction set is. And I'm gonna put this in the heap. And it has to be in the heap because the process text is read-only. You cannot just write stuff to it, right? Process, if you don't know, has like many sections. There is the text, which is the code. There is the data, which is the static global data variables. There is the stack and heap, right? So heap is this, it becomes an area where you can put junk, memory stuff, any allocation goes there. So the just-in-time compilation code that is compiled by the V8 or the Python, or again, I keep saying Python, by Java or whatever the JIT compiler, goes into the heap. But then the OS has to actually mark this area for security reasons. Like, okay, you can now execute from this area. Otherwise, you get all sorts of, that's how, stack buffer overflow attacks happen. Right? So normally you don't really execute code in the heap. It never happens. But that's why you have to give like a permission, right? This area in the heap is actually code. Yeah? So once you give this permission, then what you do is like, all right, all you have to do is just point the program counter to that heap and address, and the rest is just history. You're executing native, beautiful machine code. So that's just-in-time compilation. So you take a little bit of an extra hit, compilation in runtime, if you will, but then the rest of the code becomes really fast, So that's what I wanted to talk about. Interpreted versus compiled language. I'm pretty sure I missed a lot of other topics as well here, but I thought I'll talk about that. You guys take care.